What is happening, everybody? Today I am doing another collaboration video with Algebro.
Hi, it's me, Algebra. We both solved this problem. It's a spoiler alert, Dogmathic ended up using cyclic subgroups. His video is shown first. After that, my video is shown, and I use one of Euler's theorems. I forgot what it was. I think it's Euler's one of Euler's theorems. You'll see when you get to it. But thank you, Dogmathic, and I hope you all enjoy the video.
Problem to work on, and I thought I'd do it more in the spirit of how he does it. It's pretty inspiring to watch him work through a problem. So I'm not that prepared. The problem he gave me was if, where is it? P divides a squared plus 1, and these are integers, of course, that we want to prove that P is congruent to 1 mod 4. Okay. So again, this is a collaboration video. I think this time we might edit these together so you can see a little bit more about how we think of these. And might be longer, maybe more boring. I don't know. We'll try it out, see how it goes. All right, so my first instinct then is to look at what a squared might be mod 4. The reason is because I've done videos where I've proven that squares are pretty well behaved in even mods like 2, 4, 6, 8. So let's look at a squared mod 4. So 0 squared, because mod 4 is really just z mod 4 is 0, 1, 2, 3. So, I mean, it's finite, it's small. So we can say 0 squared is congruent to 0, 1 squared is congruent to 1, 2 squared is congruent to 4, which is just 0, and 3 squared is congruent to 9, which is 1. Oh, another thing. Yeah, P is a prime number greater than 2. I think it says odd, which is always an interesting way to define primes, is to say it's not 2 is this the same as saying that it's a odd prime. So P is just a prime number that's not 2. All right, so I have these things. So a squared, if a squared is 0 mod 4, that means that it's either, well, it's even, right? So that means a is even. And if a is even, if I add 1, I get odd. Okay, so that makes sense. If a squared is 1, then it's odd. If I add 1 to an odd number, I get an even number. 3 plus 1 is 4 is even. 5 plus 1 is 6 is even. So by this thought process, a squared has to be 0 because that's all we have. So that means a squared is even. So which means a squared plus 1 will be congruent to 0 plus 1, which will be congruent to 1 mod 4. So far, so good. Okay, so P divides a squared plus 1, and P is an odd prime. That's why we required a to be even. So if I add 1, we have something that's odd. Now I can put P in, or a squared plus 1 in terms of P. By definition, anything that divides something is an integer multiple of it. So pk, let's say, is a squared plus 1 for some integer k. Does that get us what we want? Well, then we have pk is congruent to 1 mod 4. Okay, so pk is congruent to 1 mod 4 means that, well, again, we only have 4 options, right? So p or k cannot be 0 because 0 times 0 will be 0. So 1 and 3 would be 3. So p, k, well, p can't be 1 and k can't be 3. So we have a can of a combination of 3 and 1. So no 1 and 3 combination. We could definitely have a 1 and 1, right? I think that's ideally what we're trying to get. So p equals k equals 1 works. And if that's it, we'd be done, right? Because 1 times 1 is 1, 1 is congruent to 4 mod. And then p is 1, so p is congruent to 1. Are we done then? No. 3. 3 times 3 is 9 is, what did I have? 1. Ah, shit. So 3 times 3 is congruent to 9 is congruent to 1 mod 4. So that means that I can have p equals k equals 3. So that doesn't work. So p can be 3 and certainly not 1 mod 4. So that's, is that a dead end then? I usually like to think of these things with mods and squares. Obviously, I like to think about the square being 0 or 1s. If barring that, I generally look to see if I can do some manipulation in Chinese remainder theorem. I've done a bunch of videos on Chinese remainder theorem. I also like structure. Mods are structured nicely. I don't think, what if we looked at this? I don't know if Algebra should edit out the parts where I'm just staring at the screen. I'll leave that up to him. Do we have to abandon this track? I think we might. Just because we have an integer multiple of our prime, and then we have 2 possibilities, it doesn't necessarily force it to be 1. I can't just assume k is 1. There's nothing that leads me to say that k has to be 1. All right, what if we look at, no, that won't work. How about we start over? All right, so we have p divides a squared plus 1. We want to show that p is congruent to 1 mod 4. So we started with a squared being mod 4. What if we looked at this mod p? Because p dividing a squared plus 1 means that a squared plus 1 is congruent to 0 mod p, where p is prime. And again, not 2. So p is prime. Prime mods are nice. They behave well. Everybody likes a good prime mod. Well, a squared is congruent to -1 mod p. Of course, p is congruent to 0 mod p. What do we we know about mod P's? Oh, if I square the square, I get a to the fourth is going to go into 1 mod P. What are the representatives mod P? Maybe that one help. Integers mod P, 0, 1, 2, dot, 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 all the way to P minus 1. Feel like I'm producing a lot of dead air. Oh, shit. Oh, oh. Okay. I like groups. I like group theory. So let's see where that leads. So notice I have a Z mod P. If I collect the units mod P, I have this lovely set of reps. And that forms a group. Now I know that, let's see if, so I did a, was it a, I think a short on a cyclic group. Did I? Yeah, so I did a cyclic group short. I don't remember exactly. I think it was 7. The cyclic group generated by 7 mod 11. I don't remember. But the gist behind a cyclic group is that I have some element. So if I have 2 and I want to generate the cyclic subgroup of a group, because this is a group, I can take this and square it, right? So I take 2 is in that group, 2 squared is in that group, 2 to the third is in this group, and so on. And that's 8, 4, so on. So can we produce a cyclic subgroup? Because I think that we might be able to use something cool. So what does A generate then? Well, we know from above that, okay, I think this is it. So I get A squared, I get A to the third, and I get A to the fourth. And let's see if that's it. So A squared is congruent to -1. So that means that I have A -1. We know that A to the fourth generates 1. Now, generally in cyclic groups, this is going to mean that A to the fifth, well, let's look. So the A to the third is congruent to A squared times A. A squared is congruent to -1 times A. So this is -A. So A to the third is -A. So A, -1, -A1 are all unique. What's A to the fifth? That's A to the fourth, which is 1 times A, which is A. So we're back to where we started. So yeah, this is a cyclic subgroup. This is awesome. Usually this will take me a half a day, so this is awesome. It's probably because I just did that cyclic group stuff and I was thinking about it. All right, so that's a cyclic subgroup. So the order of A is 4, and the order of the parent group is P minus 1. Awesome. So note, I don't know if I put this in my short or not. I really got to write stuff down. I made a lot of videos, not as much as Algebra. He's in the high 200s, I think. I think I made 90. But one of them was, again, the cyclic subgroups. And the order of a cyclic subgroup always divides the order of the parent group. And I say parent group, I don't know if that's an official term, the group and the subgroup of the group. So A is a subgroup. Now, I'm not going to prove it's a subgroup. I suppose if I was thorough, I would prove that A is a subgroup. That's a subgroup notation. So the element generated, or the set generated by A is and it's obviously a subset, because whatever A is, that'll be in the units mod P. So it's a subgroup. I know that the cyclic group is, or cyclic subset generated is a subgroup. So I know these two things are probably true. I suppose I could prove that. But now I know I have this lovely theorem, which I always forget who did it. That if the order of a group, so if H is a subgroup of G, the order of H will divide the order of G. And if I have a subgroup A, the order of A will divide the order of the parent group. So in other words, that 4 divides, because the order is really just the, well, I don't want to say that. The order of the element A is 4, but the order of the group is 4. I'd have to think if that is always going to be true or not. But this gets us where we want to go, at least for this problem, because 4 divides P minus 4, right? Which is the same as saying that P minus 1 is congruent to 0 mod 4, right? So if 4 divides P minus 1, that in terms of mods is that P minus 1 is congruent to 0 mod 4. And this gives us exactly where we want to go, because then that means that P is congruent to 1 mod 4. Now, the only question is whether or not we actually have a group, subgroup. If we do, then we're good, because I can't check if P is I think this works. I think it does. I know that I have these 4 elements. And I know what they generate: a squared, a to the 3rd, a to the 4th, a to the 5th. Yeah, so this is a group. All of this, it's closed. It'll be fine. It'll all generate. They'll all have inverses. Yeah, that works. I don't know why I'm hesitant, but I think that's it. I think that once I get this cyclic subgroup, I can use this theorem. And the theorem I could turn back into a mod. Now, what might be the issue with this? I mean, I gotta be honest, the first track that was on, I thought that was better. I thought that was just gonna lead to what I wanted. But I think this is okay. Maybe I should just leave it. I don't know how long I've been recording. Yeah. Maybe if Algebra wants to fast forward some of this stuff, that's cool. Like, I'll call that good. So if P divides a squared plus 1, yeah, P has to be at least 5, right? Because let's say P is 3, because 3 doesn't work, right? 3 is not congruent to 1 mod 4. So that's impossible. And 3 minus 1 is 2, and 4 does not divide 2. So this tells us that P has to be at least 5. It can't be 3, right? Because a squared will always be positive. P can't divide 1 because P is prime. P can't divide 2 because it's odd. So the smallest A is 2. So 2 squared is 4 plus 1 is 5. So that, yeah, this works. That was the only thing I think that might be a hang up, is that if P or 3, because 3 is an odd prime, that none of this works. But since A has to be at least 2, 2 squared plus 1 is 5. Does that mesh with this earlier stuff? Maybe that's what I can use this for. Because A has to be even. I think so. I think my logic is sound there. Yeah, we'll call this good. Put a little box. I'm done. Yeah, awesome. So I think that works. So I used cyclic subgroups, which honestly I didn't think that was going to happen, but all right. Yeah, great, awesome. Subscribe to both of us. I'm Dogmathic and Algebro, and I don't know which order he's going to edit this, but that was fun. I've never done this where I'm just train of thought. If he wants to edit through this, that'd be fine. Again, he is Algebro, and I will put a link in the description for him, and that's it. Awesome. Thanks for watching.
Now it's time for my video. I spent a while trying to solve it, so I eventually gave up on that strategy and looked up some stuff relating to this, and I found a theorem in which I applied to get a proof. Thank you for watching, and the following segment is my video. Okay guys, I did some research. I don't know if I'll show the previous parts of this video, but this is a collab with Dogmathic. He's a great YouTuber. He's very informative. I'm more of a student. He's more of a teacher. He's solving the same problem as I am. I believe this will be edited together with his video. But so this is the question. P is an odd prime. There's exists an integer a where P is a prime. There exists an integer a such that P divides a squared plus 1. Prove that P is current to 1 mod P. Okay, so if we, I spent a while trying to solve it. I couldn't get anywhere. So I found this theorem, and it said it would help with this problem. So, if we take this, we know that our P in fact is a prime, and P, in previous segments I proved that P does not divide A, I believe. But let's look at this. P squared, if this divides P, if A squared plus 1 divides P, then we know that A squared over P plus 1 over P, and then this is an integer. We know that this is an integer, which means, and of course 1 over P is non-integer, which therefore means that A squared over P is non-integer. And since A over P times A over P is equal to A squared, we're seeing that that is not an integer. Can both of these be integers? Let's think. That's not how it works. I did that wrong. Because we're to end up with p squared in the denominator. So, if a squared is not an integer, a squared over p, sorry. Can we say that a hmm, because take for example, 30, okay, well, of course a squared goes into its factors, a1, comma a2, comma a3, just a1 squared, that, and then they're all times each other. A is equal to a1 times a2 times a3. If we're saying that p is not one of these factors, then I think it follows that p is not one of these factors. Right? Let's find a real number example. If p, let's say, is 3. Well, p can equal one of these, of course, because they're square numbers. But let's say p is equal to 3. And this is equal to 36. If p divides a squared, if p doesn't divide a squared, then p is none of these factors. But p a1 times a1, I'm going to use a2 times a2, a3 times a3. That's easier to comprehend for me. So p is none of these factors. Then it follows that, of course, p is none of these factors, because it's not a1, a2, a3. Yeah. So that follows that p, a over p is not integers. Okay, so we have set this up that we have a prime p does not divide a. Then we need to go to a to the p minus 1 over 2. It's equal to negative 1 mod p, then x, there exists an x such that x squared is equal to a mod p. If it's equal to negative 1, then there does not exist an x such that blah blah blah. So, I have a feeling that we need to use mod 4 here. Because we need a to the p minus 1 mod p. No, we don't need that. We can do whatever we want with this. We just need to plug the numbers in, but we can manipulate this however we want. And then eventually, that will lead to 1 or negative 1 mod p. Okay, that makes sense. Okay. So. So this is really the square root of a to the p minus 1. Let's say this is equal to negative 1. then how does a to the power of something from -1? Excuse me? -1 mod p. I am so slow. So p minus 1 is going to be even. There's p minus 1, yeah, it's going to be even because p is odd, which means over 2 that this is a to an even number. So this is always going to be, or a to an integer. So that makes sense. I'm just trying to comprehend this right now. Um, I think we also need to think, plug in p with its mod 4 variant, then we get 1. And of course p mod 4 can only equal um, can only be one of these two, 1 or 3, because if it was 0 or 2, it would be divisible by 4 or 2. We know they're odd, so it's not that. So can we say that a to the p minus 1 over 2 is -1 mod p? Well, okay, a to the p minus 1 is just some kind of integer, a to the k. Right? So a to the k mod p, we don't know. We know that if 2 divides k, then we can change it to a squared, a to the k squared mod p. And we know that is equal to -1. Oh, okay. Getting somewhere. Right, because we know a squared plus 1 mod p is equal to 0. So a squared plus 1 mod a squared mod p is equal to -1. So if a squared is equal to -1, we can say that a to the 4 mod p is equal to 1. We can say that a to the 6 mod p is equal to -1. Okay, that's something. So this is if a squared to the k and a squared to the k, a squared to the 2, a squared to the 3, a squared to the 4 would be congruent to 1 would be congruent to -1. be congruent to 1. Okay, so if we look at p minus 1 over 2 mod 4, if we say that this is okay, so then let's just say this is equal to k. We have p mod 4 is equal to 2k plus 1. Let's say p mod 4 is equal to 3, which is the first case is equal to 2k plus 1, 3 mod 4. So then we have 2 mod 4 is equal to 2k, which gives us 1 mod 4 is equal to k. So that gives us our exponent is equal to Could I just plug that in? Yeah, I could have. I don't even have to have the k. I could just plug what p mod 4 is in. So then plug 3 in. So p is equal to, is congruent to 3. This gives us 2 over 2 is equal to 1 mod 4, which gives us odd, of course. Then p is congruent to 1. Then we get 0 over 2 is equal to 0 mod 4, which is even. We want to show that's equal to 1, so let's look at the even ones. Even ones, we get 1. For 1, we know that there's an x such that x squared is congruent to a mod p. Okay. How does this help us prove that p divides a squared plus 1? Well, there's an x such that x squared is congruent to a mod p. So a mod p is a square number. The residue when you divide a by p is a square number. And we know that a squared plus 1 over p a squared plus 1 mod p. Can we show that a squared plus 1 mod p is congruent to 0? We square both sides and add 1, we get x to the 4 plus 1 is congruent to a squared plus 1 mod p. Okay, I'm gonna pause this, I'm gonna take a break, and I'll come back. I was looking at this formula again, and I think I interpreted it wrong. But you plug in for a as a number that you think that you're testing this number to be what it's called a quadratic residue, which is testing this number to see if when it's squared mod p to see if that's a possible value. So if it's 1, then it is a possible value. If it's -1, then it is not. So if we use -1, we know from this that a squared mod p is equal to -1. So we know that there exists some value a squared mod p which equals -1. So for here, let's plug in a is equal to -1. That means that a, -1 to the p minus 1 over 2 is equal to 1, which means that p minus 1 over 2 is equal to over 2 is an integer, meaning that p minus 1 over 4 is an integer. If we plug in, if we use mod 4 here, if we plug in, if we use mod 4, then we say 3 minus 1 over 4 is equal to 2 over 4, which is not an integer, which means that it can't be this. If we plug in 1, we get 1 minus 1 over 4, which is in fact, or it's really asking if it's an even number, but that is an integer, is equal to 0. So, that means that because this is called Euler's criterion, through Euler's criterion, we see that -1, by rearranging this equation, we see that -1 is a quadratic residue. But plugging that into Euler's criterion, we get that 1 to the p minus 1 over 2 has to be equal to -1, which means that p minus 1 over 2 must be even, which means that p must be congruent to 1 mod 4. Therefore, proving that if p divides a squared plus 1, p is congruent to 1 mod 4. Yeah, that's done. Go check out Dogmatic's channel. This was a long one, and it was difficult, but very insightful, and it was fun. I want to check out his channel, and this probably will be edited together with him, so yeah, you'll see him. Have a good day, guys. Thank you for watching, and bye.